Okay, so good morning, everybody, and let's begin our second class. So this will be maybe the I I believe it will be the last pretty dense class because I want to kind of prepare us for actually the machine learning. So we need to. So last time we covered just general ideas. Today we will cover main tools like NumPy and Pandas, but later on we will just apply these tools. So uh, not every class will be very advanced and with problem solvings. So plan for today is to learn how to choose the best k for k nearest neighbors, then modification weighted nearest neighbors. So you will be prepared for the first homework. And then we will do coding problems on NumPy and Pandas. So let's see. Okay, how to choose the best K for nearest neighbors. Uh, so last time we talked about training data, and we used this training data features and targets um, to classify a new point by a distance from a new point to k nearest points. By test data, we mean the set of points that we don't use for prediction. So again, they will have some indices xi and yi, but the I will go, for example, from n+1 up to some other number n. So, and then we can make classification. We can make classification and calculate accuracy on the testing data. So what we did last time, we made prediction for, which is called leave one out. We considered, like in the second problem, we considered one point as unclassified and used other points to classify. But in practice, we actually use a new data points, not from our training data. So we calculate accuracy on the testing data, and we can do this for different case. For example, you can do this for k for one neighbor, then you can do this for two neighbors. Remember, it's tricky because sometimes we have two neighbors with different classes, and then we can flip a coin and to choose which class to assign to our point for three neighbors and so on. And also we can calculate accuracy on the training data. Also for K1, K2, and so on. And then we can plot these accuracies. And the plot, yeah, so this is how we split our data. Typically, we will later, we will also add a validation set, but for simplicity, for now, we will just split in two parts. There's also cross-validation, but we will talk about this later. So we plot this accuracy for our points from the first part of our data set and for the second. If we take just one neighbor, then on the train, each point will be the neighbor of itself, because in training data, every point will coincide with one point from training data. And then, of course, the prediction will be 100% because we will classify the point by itself. So that's why the accuracy is 100% for one neighbor. But if we use one neighbor classification on the new points, then accuracy will be pretty low. Then the best case, we will choose where this plots intersects. So when the accuracy on new data coincides with accuracy on the training data. So this is how in your homework you will just write a for loop and choose the peak, the maximum of the orange line, and this will be the best case. Okay, now we will go to the second topic, which is weighted k-nearest neighbors. And this is the plot that I expect you plot in your homework. The decision boundary, the blue points and orange points are given our training points, but you can choose arbitrary point on this plane and classify based on the neighbors of this point. So that's why the entire plane actually has colors. Every point which is unlabeled is the testing point. Okay, so I want to go back to this example, and let's consider 5 nearest neighbors. So what was the classification for 5 nearest neighbors last time? Do you remember? As a square or triangle? But what do you think? Is it does it look good that we classify this green point as square, or maybe it's closer to triangles?
It's closer to 2 triangles, so it seems a little weird to classify it as a square.
Yeah, so we how can we fix that?
You could weight it based off the distance to each of the neighbors.
Yeah, and this is the algorithm for weighted k-nearest neighbors. So we will assign, for example, we take 5 neighbors. We can assign the weight to the closest point as 1. The weight to the second close point is 1/2. The weight to the next close point is 1/3. So just we can add some scaling factor that will make the larger distance smaller. And let's go to the formula. So this was the classification without weights. Just we count the number of red triangles and the number of blue triangles. But we can introduce the weights. Well, in this example, it's not just 1 over n, it's n minus 1 over n. So 5 over 5 for the closest point, 4 over 5 to the next, and so on. So if we will add now these numbers, ones and zeros, but with coefficients, then this sum for blue squares will be smaller than the sum for red triangles, and we will classify our point as the red triangle. Does it make sense? Yep.
How do you model which is the best way how to do the weights? Like, do you make it so it's just as the
Even how we choose the weights, the formula for weights?
yeah, is there ever a reason why you would use like an exponential weight over a linear weight like it's like shown in the example?
Yeah, so this is actually, we will answer this right now, how to choose the weights function. So this is just to give you an idea how you can come up with your own weights, like 1 over n or n minus 1 over n or n minus I over n. But the idea is to choose the weights such that they decrease. And if we draw, for example, the number of neighbors, for example, K, and the weight W of K, then, for example, for the first, and if we index from 0, then it will be 0. For the first, it's reasonable to choose the weight as 1. For the second, for example, smaller. And there was a reasonable question. How we choose the decay? We can choose this linear. We can choose that exponentially. So what is better choice? And typically we will choose as Gaussian the decay for the weights. And so this is just a sum function of k, but it's defined also for any real number. And the only property of this function is that it should decrease. And typically, this function is called kernel. So here are the different formulas for weights. The first one is linear. The second one is exponential. When we take, for example, a number smaller than 1, for example, 0.5, 1/2, then it will be 1/4 for the second, then it will be 1 over 1,000 for the 10th neighbor, so it will decrease. Or you can choose a function, I denote this f, but this function is k capital. A function, and the argument of this function is the distance, and there is also hyperparameter which is called window size h. And here are examples of the different choice of h. So yeah, here I'm taking the Gaussian function, the e to the power negative squared, and if h is so what is our formula is actually distance over h. If h is 1, then it will be just proportional to the distance. Let's think about which plot corresponds to the larger h and which plot corresponds to the smaller h. So if our h is, for example, 1/2, if our h is 1/2, then this function will return the value at the origin for wait, not at the origin, for example, at 1. When the distance is also quite small. So it will be so for example, if it was 1 for distance d, now it will be 1 for distance d over 2. So it will correspond, so high value will correspond to the smaller distance. So it will be the second plot. If our h is large, like for example 10, then the value at 1 will correspond to distance 10 times larger. So for larger distance, we will have the value that we had at 1. So the answer is that for larger distance, this decay will be slower, and for h, and for smaller h, the decay will be faster. But in your homework, I asked you to use just linear, just 1, then 4 over 5, and so on. Okay, now let's go to the coding part. So if you go to the course page, there is a link to the GitHub, and in GitHub there is the link problem set 3. So if you click on this link, or you can click here, you can copy this path, this URL, and open Google Colab. We will use online interpreter Colab. So when you open Google Colab, you can choose GitHub here and paste this path to the notebook. So copy the link and then open Google Colab, choose GitHub tab, and paste this link there. When you press magnifying, yep. Oh,
Yes. Like this. Very cool.
Yeah. Do you know how to open the GitHub with course?
Yeah.
Yes. So if you go to week 1, here is uh, here, here are the links. Yes. But also I published link on my courses just in case. So because after we solve this notebook, I ask you to submit by the end of today. And there is the Dropbox on my courses, just this notebook. So, and now we can open, you can just press enter or open from here. So when you close this, the browser, it won't be saved. So when you finish working, you will need to go to File and save, for example, download as Jupyter Notebook, and this file you will upload on my courses. If you just close, you will lose all the data. Or you can save on your Google Drive. So we will use today NumPy and Pandas, and also Matplotlib for to plot to visualize information. So how many of you guys worked with NumPy or Pandas? Oh, just like half. Okay. So just a short introduction. NumPy has its own data type, which is called NP array. And these arrays are very convenient to work with because you can multiply, for example, the array by a number, and every element of this array will be multiplied by this number. You don't have these properties for lists in normal Python. Let's create array or just, so I create a list and then I cast this to array to an NP array type. You can have access as slices as a normal list, for example. Oh, here I want to show that if I change the, so it's the same as with lists in Python. They work like the links. If I create a new array from the array A, and then I change an element in array A, it will be changed also in array B. If we want to separate our variables, we should use dot copy or deep copy as we work with lists in Python. The size of our array you can check with. Oh, by the way, to run the cells, you can use shortcut Shift Enter. So instead of clicking on this run, you can just use press Shift Enter, and so on, and you will run the array. Our array A is kind of zero-dimensional. If we want to have one-dimensional array, there is the method reshape. For example, in reshape, I can indicate the number of columns and the number of rows, and then, sorry, it will be two-dimensional array. let's see. Oh, I had 3. But if you don't want to calculate the length of your array, and you know that you just need in this case just one row, you can use -1, and it will reshape your array such that it will have one row, and whatever the number of elements, it will be the number of columns. If you want to have one column, you can do 1 for the number of columns and -1 for the number of rest elements. You can't transpose one-dimensional array. That's why we add additional dimension, because if you apply transposition to just one-dimensional array, 1 to 3, it will remain unchanged. But if we add a new dimension, then the transposition will actually, oh, this is A. Yeah, so A wasn't reshaped. But if I apply this to B, then it's transposed my vector. So from column, it created the row. NumPy has also random numbers generators. So I think we will just run this quickly. So here I generated a matrix of size 4 rows by 3 columns. You can reshape it into one long row. You can also calculate some statistics along only columns or only rows. For example, this function max will calculate the maximum along columns. So because axis is 1 second. So if we look at the first column, sorry, along columns. So if we look at the first row and we go along the columns, then the maximum will be this number. For the second row, the maximal value will be this one. So if we indicate x as 0, it will take maximum along each column, so it will go along rows. The main important thing that we will use today is called broadcasting. So broadcasting means that if we want to add a number, for example, to our NumPy array, it will be added to every component. Even if it were like matrix, it will add this number to each component. Then, if you want to add a column to a matrix, for example, A1, A2, A3, B1, B2, B3, C1, C2, C3, and you add a column, then broadcasting will add this column to every column in your matrix. And this what you don't have in normal Python list. And so on. If you add a row, this row will be added to every row of your matrix. So it's very convenient. Instead of writing for loops, we will use just broadcast. And in example here, I add to my matrix C this array, and I believe, I don't know, maybe we will get an error because this array is one-dimensional. Oh no, listen, no, it actually works. So how it works? It added. Just to double check, I will reshape this array and compare the result. Yeah, it added one-dimensional array as a row, but if you don't want to guess every time how it will add as a row or as a column, it's better to reshape in advance. And if I reshape this as a column, then I'm okay. They have different shapes because I have a matrix 4 by 3, so I can't add the 4 rows or 3 rows to 4 rows. So it didn't work. But if I change, for example, the axis here, then it will work. So if you remember how broadcasting works, then it's easier just to reshape your one-dimensional array. So you always remember if it will be added as a row or as a column.
When I'm running this, I get a message saying that like the variable is not defined. Because the yes, so like when I run these the exercises, I get the error message saying that the name for the variable is undefined.
Yeah, I think that you skipped, maybe you didn't run one of these lines. So check if there is a number. So, or try just to run your code from the beginning, like just every line. Maybe just one line was skipped where I defined B. I don't know. So a matrix multiplication. Just try to run from the beginning, okay? So if we use the asterisks, then it will multiply element-wise. Just each element will be squared. If we want to multiply as matrices, then there is common matrix multiplication. Then it will multiply a matrix, in this case, 4 by 3 transposed, so it will be 3 by 4 times 4 by 3, and the result will be 3 by 3. But the easier, like shortcut, which I prefer, is just this add comment. And this add comment stands for matrix multiplication. Instead of writing NumPy matrix multiplication, you can use add. So asterisks is element-wise, add is matrix multiplication. There is also comment dot product, and this comment will multiply your matrix by even one-dimensional array. This in new version, actually, this matrix multiplication also works with if C is one-dimensional, but in earlier versions, it will give you an error. You can change the type of your elements. Then, okay, now we arrive to the first problem. So in k-nearest neighbors, we want to calculate the distance from a new point. So let's think about these matrices as the features for there is a let's see. So let's oh, there is a misprint. Here should be two. So these are the features for the first element. These are the features for the second. So this should be two. Fix it now. Mhm. Okay, so here is our data. The features for the first point, the features for the second, and so on features for the third point. Now we have the testing data. And again, we have 5 points here, 5 points. For our k-nearest neighbors, we should calculate the distance from the first point y to every point in our training set. So we should calculate 20 numbers. For this, and then you remember, we should sort by these points by distance and choose the k-nearest points. For the second line, we also should calculate the distances to each point here, and so on. So we should calculate 5 times 20 numbers. And the first task for today, to calculate this okay. There is one more thing. In this case, it looks like X was actually the testing step because I have. Sorry, let's calculate the matrix D transposed because I want to have 5 rows and 20 columns. So the first, so this column will be our row. I don't want to retype this matrix for now. So in the first line, I want to have 20 distances from the first point y to every point in my matrix X. Does it make sense? In the second line, the 20 distances from second point y to every. And the task is to write this just in one line using broadcasting. So we want to calculate. So what I want to calculate? I want to calculate. Okay, I will explain a little bit. So we have a matrix 20 by 3. So it will. Oh, okay. Let's just make it okay. Sorry about that. This matrix is transposed. I want to calculate the first. I will take matrix B because I want to have 5 rows. So this first matrix I will reshape in 3-dimensional array. So this will be matrix B with 5 rows for y1, the first coordinate, and so on. We had 3, so y3 with so the first point and the third component. But in general, it can be arbitrary number of features. The second line will stand for y2. Again, the first component and the last component. And the last row will stand for y5. And I want to calculate the Euclidean distance, so the square root of the sum of square differences. So y1, y5 with index 3. So I will subtract the matrix A, but I will reshape matrix A as follows. So this will be 20. And this dimension will be 3. So this will be x first, the first component, and so on, x first, the second component, or the last component. Then the next element, like, what's that row, will be x2, the first component, so on, the last component. And so on. And the last will be x20. And now let's try to subtract this using broadcasting. So we just subtract these two arrays. So what will be the result of the subtraction? So this will be kind of 2-dimensional broadcast. First, from my first y1, every point x will be subtracted. So for the first level, for the first line, I will have 20 differences. So the result will be a 3-dimensional array. And here I will have the first component of the first point minus the first component of x1. And here I will have the third component of y of the first point y1. Of course, you could do this with 4 loops to calculate with 2 for loops, like one goes through y's 5 times, another goes through x's, but now we will write this without any for loops. And it will work faster, actually. So minus the third component of x1. So I subtracted the first row from x from the first row of y. Then I will subtract the second row of x from the first row of y. And now you can guess, you can see now the differences. We can take the square of this matrix, we will get square difference, then we will sum over this third dimension, and we will get the sum of squared differences. And finally, we will take the square root. So this is the main idea. So if you have any questions, feel free to ask. So the second line will be y1 minus x2. I will skip writing the indices. I hope you understand that it will be the second line and so on. And the last will be y1 minus x20. Now, the same will happen with the second line. So y1 minus x20. In the second line, we will have y2 minus x1, y2 minus x2, and so on. Okay, so how we will write this in code? The first thing is to so when we get this matrix, we will just take the square of this matrix and sum along the third dimension, and it will be the sum of squares. So we will get 5 by 20 numbers, exactly what we actually. For now, it's 5 by 20 by 3, but after summation, we will get 5 by 2. So there are two ways to add a dimension to your matrix. You can do reshape. So to get the first matrix, you should reshape your matrix B as what will be the first dimension? X1. The second dimension, oh no, sorry, the first will be 5. The second will be 1. And the third will be 3. So you can just type b dot reshape, for example, minus a dot reshape, and a will have x will be 1. The second dimension will be 20, and the third dimension will be 3. So, but instead of reshape, you can use this syntax b let's see, b, I believe. Wait a second. There's very simple syntax. Oh, none. Okay. None. And so instead of writing reshape, you can add a new dimension using none, and you can see the result will be exactly what I want. So, and minus a, and it understands what I want to do. And if you look at the shape of this result, then it will be the shape of this three-dimensional matrix, 5 by 20 by 3. So the next step is to raise power 2 and sum over the last dimension. and you're done. Well, and take the square root in the end. So I can wait a little bit and I can type the result. I think the main difficulty was to come up with this three-dimensional matrix. After that, you just take the raised power 2. So after raising power 2, every difference will be squared. So you just can write here power 2. So every difference will be squared. And after that, you should sum up along the third dimension. And to sum up, you remember it is np.sum comment axis equals the third dimension will be 2. And finally, so this will sum up along the coordinates. And finally, to get the square root, you can just write np.sqrt. And this is the answer. And you should get the matrix 5 by 20 that contains the Euclidean distances from every point y to every point x. In your homework, I asked you to calculate Manhattan distance. So you will figure out easily from this example how to modify this to Manhattan distance. And when you run the scikit-learn built-in k-nearest neighbors, it will work actually longer than your implementation without for loops. Okay, if you have any questions, just raise your hand. And oh, by the way, these problem solvings, they are not individual. You can communicate, you can look at the other's code and so on. So feel free to talk with each other when we do or paper or coding problem solvings. Because it's just practice. But if you have questions, raise hand and I will come. So this, if you are done, the second problem is straightforward. I plotted the parabola. So here's the plot of parabola, and I plotted the contourplot. The contourplot is the section of the parabola with a plane. So if you make a section of the parabola, you will see a circle. And this will correspond to Euclidean circle. And I asked you to change it to Manhattan, to L1 circle. So instead of x squared plus y squared equals 1, to plot the surface absolute value of x plus absolute value of y equals. So just change a little bit my code. I think it's straightforward. Instead of squares, just absolute values, and you will see the the circle in Manhattan distance. Actually, I can do it with you. Can I erase the drawings? Okay. So Okay, let's see. Who knows, actually, maybe who took maybe a math class, how the circle in L1 norm will look like. Okay, if you don't know, you will see it. Oh, I think that's it. There's just one change. So this is how the surface will look like. It's not parabola anymore, but oh, wait a second. We also don't need a square root somewhere. One second. Yeah, we also don't need the square root because there's no square root in Manhattan distance. It should look like the surface should look like just 4 planes. And the section should look like this. So this is the circle in Manhattan distance. Does it look like a circle? It does. In mathematical definition, the circle is the distance equals 1. So Manhattan distance equals 1 on these lines. And it will help you later to understand the plots from the homework, but we will talk about this after the homework. Yeah.
I've been trying to run some of the stuff, but I keep getting errors, like the library is just not being defined.
Did you run the first line?
Oh,
Maybe not. Okay, now we are good to go to the next library, which is Pandas. So Pandas library is developed for working with tables. So every data analytics or data scientist works with Pandas, because you read the Pandas also supports SQL language, and so it's the tool for working with table data. And we will read this data from the notebook of the statistician, British statistician Francis Galton, who collected information about families in UK in I don't remember what is the year. Okay, in the end of 19th century. So he collected information about the number of children, the height of parents, and the height of children. And he came with this plot. I'm sorry, I don't remember which axis actually represents the height of parents and which represents the height of children. I believe this represents the height of parents and this the height of children. So, and he plot the average height of parents and the average height of children, and noticed that for taller parents, children tend to be shorter, and for shorter parents, children tend to be higher. And he called this phenomena as regression. So that's where the name for linear regression came from. So we will upload this data in Colab. Here is the file manager, and for example, you can use the Linux comments here with just exclamation sign. So you can upload the data from your computer, or you can upload from the internet. So in this case, I upload directly from the internet. And typically we use comma-separated files, CSV files. To plot the data, so in NumPy, the type was NumPy array. In Pandas, the type is data frame. The table has type data frame. So to visualize data frame, we can we can print just the F, but typically we use df head and it prints the first 5 rows. There's also data frame tail, which will plot last 5 rows or whatever number you will indicate. So this information contains the index of family, the heights, I don't know what are the units here, of parents, gender, and the number of children, and the height of each child. The first step to understand your data is to plot data frame in 4. Data frame in 4 will provide the summary of your columns. And for example, gender was not numerical. That's why here is the type object. If you see something that is not integer or float, you should change this into integer or float because we want to work with numbers. Describe will provide some statistics. Okay, we have 5 minutes. I will go faster. Here's how you can create a data frame from dictionary. Let's skip it. Columns is a list of your features. Dot index is the list of your rows. In our case, these are just numbers. And if you want to access by index like 1, 2, then we use command ilog. So one stands for this line, and 2 stands for this column. So this is the element of this matrix 667. If you want to access by the name of the column, then you should use the command log. Then you can write, for example, 1 and mother, for example, instead of 2. So I log access by index, log by value. Here's the visualization of this plot. This is called scatter plot. Blue corresponds to males and to boys, and pink to girls. You can subtract the average, and then these plots will overlay, and then you can work you can use for analysis both data and for boys and for girls, so you will have more data. So there's common drop, and drop, you can drop, for example, column, then you can type data frame drop columns, okay, columns. So it drops the column, but it doesn't change the original data. If I print the data frame again, you will see the column height there. if you want to drop this column from the original data, you should indicate in place equals true. By default, it's false. So yeah.
Why do we have an axis there for the draw function? Why do we have an axis there for the?
Oh, no, it's a different syntax. So you can use this syntax, but this syntax is more straightforward. So you can also drop using command del and column name. It also will work, but it will be in place operation. It will remove from the original data. Great. Now, what we can do with columns, we can, for example, look at the entries of our column, and for this we can use unique, and it returns just unique values in this column. And how to map these letters into integers? We can use function map. We can use function apply and use lambda function inside. And for example, map takes the dictionary and applies this dictionary, and then I created a new column, and this new column contains the code instead of the character now. Okay, our first. Oh, okay. The last thing is group by. So we can group our data by any field. In this case, I grouped by gender and calculated the mean height of boys and girls. So this is how we can do this using group by. Okay, the first problem. What is the fraction? Okay, we have just 5 minutes left, but I think it's fine. We have just 2 lines. What is the fraction of families with 3 or more children? So we can group by which field? df group by, well, but you see, Colab actually provides the answer. So we group by the first column, family, because you remember the first index was the index for the family. So we group by ones, we group by twos. So it will group by the families. Then it will take the column the number of children, but I want a fraction. So how we should modify a little bit if I want a fraction, not a count. Yeah, but without division, you're right. We can divide by the total length. Mean. Just oh, wait a second. It's something wrong. Group by family. Oh, I also should check. Sorry, before mean, we should check that it's greater than 3, with 3 or more children. Okay, the count here was correct, I believe. Count. So here we have true or false that first family has 3 or more children and so on. And now we should sum this together and divide by the number of families, or just take the mean. And voila, the answer. The second question, just very simple. I will leave it to you. Create a new column with average height of parents. Yep. Oh, you're right. Yep. Thank you. Greater than 3. You're right. Oh, it's interesting. Why the fraction actually is greater? I would expect that the fraction of the number of children, or the number of families with the number of children greater than 3. Oh no, it's correct. We add greater than 3 is just 4. That's why the fraction was smaller. It's correct. Okay, so the last line is just to create a new column, data frame of you can call it average height, and just sum up the column mother plus column father over 2, and that's it. Okay, actually, the AI assistant helps us. Okay, that's it for today. Please submit your notebooks by the end of this day. You are ready to start working on your homework 1. And next week, we will go to exploratory data analysis, how to work with missing values, how to clean the data, how to prepare non-numerical data for our models.